Hello and welcome to MechZone. Previously we were discussing about the turbines, and in the lecture 3 we have also discussed about the various classification of turbines and how the turbines were classified on the basis of the different classifications. And from this lecture we shall be continuing from there. And the first topic that we have to study in this lecture is cavitation. Cavitation actually I have already taught you when I was teaching fluid mechanics. So when the liquid enters the hydraulic turbines at high pressure, this pressure is a combination of static and dynamic components. Static and the dynamic components of pressure I have discussed when I was discussing the pitot tube. Thus, cavitation can occur near the fast-moving blades of the turbine, where local dynamic head increases due to the action of blades, which causes static pressure to fall. And as a result of cavitation, the bubbles which are being formed, they are colliding against themselves and they are getting burst. So when these bubbles are getting burst, they are producing very high energy pressure waves, which is mainly causing the pitting action. Now we come to the net positive suction head, and the net positive suction head is also abbreviated as NPSH, and for the available we will add A. The absolute dynamic head at the pump inlet is in excess of the vapor pressure is termed as net positive suction head available. It is the theoretical amount of head that could be lost between the suction and the point of minimum pressure without causing any cavitation. So without causing any cavitation, we are considering net positive suction head available. Now we come to an important topic, that is the specific speed. And specific speed is actually defined as the speed in the RPM of a turbine which is geometrically similar to the actual turbine but of such a size that under the corresponding conditions it will develop unit power when working under a unit head. So the formula for the specific speed is ns is equals to n under root p upon h की power 5 by 4. However, if we are talking about the specific speed in case of pumps, then we would write ns is equals to n under root q upon h की power 3 by 4. So specific speed formula for turbine and specific speed formula for pumps are quite different from each other. Okay, we now come to the topic of pumps. And to define a pump, it is simply a mechanical machine or a device which is used to transport a liquid, or in general if we say it is used to transport a fluid from one point to the other under pressure. And it converts the mechanical energy which is supplied to it externally into hydraulic energy and transfers to the liquid through a pipe. Flow is normally from the high pressure to the low pressure. This point we have already discussed when we were discussing about the viscous flow or the laminar flow. There we have found out that pressure always takes place in the direction of decreasing pressure, that is the negative pressure gradient. That means from the region of high pressure to the region of low pressure. And on the basis of mode of action or conversion of mechanical energy to hydraulic energy, the pumps are classified into two main categories: rotodynamic and positive displacement pumps. And in the rotodynamic pumps, we are actually increasing the energy level, which is because of the centrifugal energy, pressure energy and the kinetic energy. And in case of the displacement pumps, the suction of the liquid is taking place and then this liquid is being displaced due to the thrust or the force which is exerted by the moving member, and as a result of which it leads to the lifting of the liquid from one level to the other or up to a desired height. We first come to the centrifugal pumps. So centrifugal pumps are a type of rotodynamic machines which are actually converting the mechanical energy of the shaft into the kinetic energy and the pressure energy of water, which is actually used to raise this fluid, that is liquid, of in general we are talking about water, from one level to the other level. And the wheel in which this conversion is realized is known as the impeller. So the wheel in centrifugal pumps is called as the impeller. A centrifugal pump is named so because the energy added by the impeller to the fluid is largely due to the centrifugal effect. We will be studying this centrifugal effect in the theory of machines. The next subject that we are going to start after this subject is the theory of machines, and after theory of machines we would be going simultaneously for mathematics and machine design, and at the last we would be going for IC engines and material science. So this would be the schedule that we will be following. Now in the centrifugal pumps, they are classified according to the working head, specific speed, type of casing, direction of water flow, number of entrances to the impeller, disposition of the shaft, and number of stages. So these are the basis on which the classification of centrifugal pumps takes place. Now on the basis of working head, the centrifugal pumps may be classified as low, medium and high head pumps. Low head centrifugal pumps, medium head centrifugal pumps and high head centrifugal pumps. When we will say it to be low, when the head is below 15 meter. When it is between 15 to 45, it is medium, and when it is above 45, then it is high head centrifugal pump. These pumps may have horizontal or vertical. These have either vertical or horizontal shafts depending upon the configuration that we want to have. Vertical shafts are useful in deep wells. The deep wells generally uses vertical shafts. Again, the formula for the specific speed has been clearly given. This formula is applicable in case of pumps, whereas the formula that we studied earlier, it was for the turbine. So please make sure that you are applying the correct formula for the correct fluid mechanic or fluid machinery, because if you are applying this formula in case of turbines, then you will get the wrong answer. Okay, now the type of casing also forms the basis for the classification, and volute chamber pump, vortex chamber pump and diffuser chamber pump. Now we come to the calculation of work done by the impeller of a centrifugal pump. Now capital N is the speed of the impeller in RPM, that is rotations per minute. Capital D is the diameter of the impeller at inlet, and capital D is also the diameter of the impeller at the outlet. U1 is the tangential velocity at the inlet, pi D1. Actually this should be D1 and this should be D2. Please make a correction. This is D1 and this is D2. U1 is the tangential velocity of the impeller at inlet, pi D1 N upon 60, and tangential velocity of the impeller at the outlet, pi D2 N upon 60. V1 is the absolute velocity of the liquid at inlet. So point 1 is corresponding to the inlet's position and point 2 is corresponding to the outlet or the exit condition. Vf1 and Vf2 we have already discussed. They are the flow velocities at inlet and outlet. Vr1 and Vr2 are the relative velocities at the inlet and the outlet. Vw2 is the whirl velocity at outlet. Alpha is the angle which is made by the absolute velocity at inlet with respect to the motion of the vane, and phi is the blade angle at inlet, beta is the blade angle at outlet. We definitely have to remember all these terms because they will be used in the numericals. Now force, as we all work as we all know, is equal to force into distance. So and for the centrifugal pump, Vw2 is equal to 0 means radial flow at outlet. So the work done per second per unit weight would be Vw2U2, and the work done per second is equal to this formula. So work done comes out to be Q upon G Vw2U2, and Vw2U2 would be 0 if we are having a radial flow at the outlet section. Next we come to the cavitation in case of a pump, and how we are going to reduce the cavitation by increasing the pressure at the suction of the pump, reducing the temperature of the liquid being pumped, reducing the head losses in the suction piping, reduce the flow rate through the pump, reduce the speed of the pump. So all these ways are actually contributing to the reduction of cavitation in case of a pump. And what actually happens because of cavitation, or what are the side effects of cavitation? Degraded pump performance, metal gets corroded, as I have already told you because of the pitting action, and this pitting action is mainly taking place because of the blasting of the bubbles which have been previously formed. Audible rattling or crackling sound which can reach a pitch of dangerous vibrations, damage to the pump impeller bearings, fair rings and seal. So it is actually causing large amount of damage to the pump body. Next we come to the reciprocating pump, and in the reciprocating pump we are actually having a reciprocating motion, and that is why it is called as a reciprocating pump. These are used to increase the energy level by means of by virtue of which it can be raised to a very higher level, and they are actually the positive displacement pumps, that is initially a very small quantity is taken and is then physically displaced and the forced out by means of pressure, and this pressure is actually exerted by a moving mechanical element. And the use of the reciprocating pump is limited these days and being replaced by centrifugal pumps. Nowadays centrifugal pumps are more preferred over reciprocating pumps. For industrial purposes they have become obsolete. Obsolete means outdated. So here we are going to learn a little bit of English words also. So obsolete is a very common word which is generally used in the day-to-day life, and it simply means outdated. Okay, and due to their high initial and maintenance cost as compared to the centrifugal pumps. Now maintenance and initial setup cost is very high in case of the reciprocating pumps. Small hand operated pumps are still used which include well pumps. So in the well pumps we are using the the reciprocating pumps. These are also useful where high heads are required with small discharge as oil drilling operations. So they are generally used for the oil drilling operations because their high heads are required and the discharge available is small. So here we can see the diagram for reciprocating pump, and this is actually the connecting rod and such that the crank is rotating, and due to the rotation of the crank, this piston rod is actually performing a reciprocating motion to and fro. Okay, so this is the diagram of the reciprocating pump, and it consists of a plunger or a piston that moves forward and backward inside a cylinder. This is actually a cylinder, and this is being connected by means of a connecting rod and then the crank, in such that the crank is rotating in a clockwise or either in the anti-clockwise sense as required. The cylinder is connected to the sump by a suction pipe and to the delivery tank by a delivery pipe. So there are two pipes, the suction pipe and the delivery pipe. The suction pipe is mainly used to suck the liquid from the sump level, and the delivery pipe is actually delivering that liquid which is being sucked from the sump level. At the cylinder ends of these pipes, non-return valves are provided so as not to allow the liquid to return back into the sump level. A non-return valve allows the liquid to pass only in one direction, that is unidirectional flow is possible. Through suction valve, liquid can only be admitted into the cylinder, and through the delivery valve, the liquid can only be discharged into the delivery pipe. Now, how the working of reciprocating pump is taking place, that is when the piston moves from the left to right, a suction pressure is produced in the cylinder. And because of this suction pressure, the liquid is being sucked from the sump level into the cylinder. And it is started for the first, and air from the suction pipe is sucked during the suction stroke, while the delivery valve is closed. The delivery valve is closed during suction, and the liquid rises into the suction pipe by a small height due to atmospheric pressure on the sump lid. During the delivery stroke, the air in the cylinder is pushed out into the delivery pipe by the thrust of the piston. Because of its reciprocating motion, it is actually producing a thrust which is used to push the liquid from the cylinder during the delivery stroke into the delivery pipe, while the suction valve is closed. Suction valve is closed during the delivery stroke. When all the air from the suction pipe has been exhausted, the liquid from the sump is able to rise and enter the cylinder. Now during the delivery stroke, it is displaced into the delivery pipe, thus the liquid is delivered into the delivery tank intermittently during the delivery stroke only. So this is a very important this is a very important thing which needs to be remembered about the working of the reciprocating pump. You should have a basic idea about how the working of the reciprocating pump is taking place, because these types of questions are generally asked during the interviews of PSUs. Now the classification of the reciprocating pumps can be done as following: single cylinder pump, double cylinder pump, triple cylinder pump, and there can be 4 cylinder or 5 cylinder pumps also. Now comes the most important part of this lecture, that is how to calculate the discharge. So I am simply focusing on the formula, that is Q is equals to LAN upon 60. It is very easy to remember the word LAN. Local area networks से हम लोग LAN को remember कर सकते हैं, LAN upon 60, where N is the speed in the RPM. Please mind, it is the speed in RPM, and L is the stroke length, that is 2 into R, and A would be the area of the cross section of cylinder. So this formula is very important and thus needs to be remembered, because the direct questions will be asked only generally from this section. Now the discharge in case of the double acting pump would be simply 2 times. So we will multiply the previous formula by 2. Now we come to the topic of slip. The slip is actually the difference between the theoretical discharge and the actual discharge, and slip is generally expressed in terms of the percentage. So Q theoretical minus Q actual upon Q theoretical into 100 would be the slip, or if we take divide the entire by Q theoretical, then 1 minus Q actual upon Q theoretical into 100. And we know that the coefficient of discharge is equal to Q actual upon Q theoretical. So slip can also be derived from the formula of the coefficient of discharge if it is given. 1 minus coefficient of discharge into 100 would be the percentage slip. Now here we have the differences between the centrifugal pump. It has centrifugal and reciprocating pumps, steady and even flow, and in reciprocating it has intermittent or pulsating flow. Why intermittent? Because it is having the reciprocating function. First the suction is taking place, then the delivery is taking place. So actually the flow is of intermittent type and it is not even flow. For large discharge in small heads, and we have seen that in case of reciprocating is generally used for small discharge in large heads. It can be used for viscous fluids, example oil, muddy water, and this can handle only pure water or less viscous liquids. Otherwise valves give frequent trouble. There would be troubling in the operation of valves if we are using a liquid which is highly viscous. Low initial cost, high initial cost, can run at high speed, can be coupled directly to the electric motor. Low speed, belt drive is necessary in case of reciprocating pumps. Low maintenance cost, periodic checkup is sufficient. High maintenance cost, and we have to frequently replace the parts. Compact less floors required, whereas need 6 to 7 times area than for the centrifugal pumps. So if we are having space constraint, then we are going to use the centrifugal pumps, and if the space is not a constraint, then we may use reciprocating pumps also. Now we come to an important topic, that is the indicator diagram. And the indicator diagram for a reciprocating pump is actually the graph which is drawn between the pressure head and the distance which is traveled by the piston from the inner to the outer dead center for the one complete rotation of the crank. So as the maximum distance traveled by the piston is equal to the stroke length, hence the indicator diagram graph between the pressure and the head stroke length of the piston for one complete revolution is generally drawn. The pressure head is taken as the ordinate, that means it is taken on the y-axis, and the stroke length is taken on the x-axis. So if we see, this is the diagram, the pressure head is taken on the y-axis and the stroke length is taken on the x-axis. HS is the suction head, HD is the delivery head, this is the delivery stroke, and this is during the suction stroke. 10.3 meters simply representing the atmospheric pressure. We have already discussed this in the fluid mechanics chapter, that atmospheric pressure is equal to 76 centimeter of mercury, 760 mm of mercury, or 10.3 meter of water, or 101.325 kilopascal. We definitely have to remember those values, because those values can be directly asked in the 2 marks question also. Because the 2 marks questions in case of GATE definitely needs to be a little bit tricky, and they also require knowledge of the formulae. So I am expecting that this question may be asked. It's not a guarantee, but it may be asked that the atmospheric pressure corresponding to height of water column is 2 marks question, and it is equal to 10.3 meter. So with this we come to the end of our fluid machinery section, and we have covered this thing in the 4 lectures. 4 lectures are designed in the absolute simplest manner as possible, keeping in mind main focus on the formulas. We request you to kindly note down the formulas on one page and look at those formulas 5 to 6 times, or after every 2 to 3 days, so that these formulas are actually mugged up, because mugging up the formulas would definitely help you to solve the problems in a better way rather than to derive the formulas in the examination hall. So with this we come to the end of our lecture. We hope that you're enjoying our lectures. Please give us your valuable feedbacks and also tell us about your problems. You can share your problems on our Facebook page, or you can comment on our channel also. We would be reverting you back within 48 hours. So in the next session, we shall be starting with the new subject, that is theory of machines. And after theory of machines, we shall be switching over to machine design and mathematics. Okay. And in the theory of machines, we shall also be studying about the vibrations also. And in the last, we shall be doing the IC engines and the material science. And we promise that by the end of November, all the technical section would be definitely complete. So thank you and all the best.